standing here without a mask, but I'm going to sit down in a minute. Let me sit down now, because that's obligatory for not wearing a mask. Glad to see you all here, and I look forward to interact the next 6 times 45 minutes with you. My name is Bart, Haar Romeny, quite a complicated name. I'm from the Netherlands. I'm an emeritus professor with lots of experience in biomedical engineering, and my field is biomedical image analysis. So I have done computer vision for almost 40 years. So I'm quite experienced in all kinds of, let's say, image analysis related tasks. And the last years, I've fully dived into deep learning. And I'll give you some slides about my background and what I go do in this course. And then the next 6 lecture hours, we go quite deep. And all my lectures will be fully interactive coding. So I show you everything directly live in code. There are no slides, there are no PowerPoints, it is just code that you see. It is in Mathematica, and nobody programs in Mathematica, maybe a few. Who's programming in Mathematica? Nobody. So what I go show you is that it is a kind of overlooked kind of software which is so easy to grasp and so powerful that it is quite interesting to show you a little bit how it works. So I also give a 15-minute course in between that you learn fully programmed into this language in 15 minutes. It's an experiment, so I really need your feedback because it's the first time I do this in a summer school in this deep session. I normally use it a little bit, but now I go deep. And please give me feedback. I'm very much used to interact with students. I'm very low threshold accessible, so please call me Bart. I'm an emeritus professor. I had lots of experience with you students, and the nicest thing if you jump on me and I didn't understand it, and can you explain this again? And please do. So raise your hand if you have questions, interrupt me. That's the best way to do. We're here just to learn. I'm here only for you. So let's do this as interactive as possible. So I already told you that I'm from Eindhoven University. Eindhoven is the hotspot in the Netherlands. 1/3 of all the money is made there. We have ASML, we have Philips, 400 startup companies there, 4 campuses, can you believe it? Our university campus. We have Philips Medical Systems, that's a big company, one of the big 3 in the world. We have an ASML campus, you all know ASML, that's the printing, the chip printing factory. They are now the biggest in the Netherlands. They made 37 billion euros of turnover last year. It's quite impressive. They make all these GPUs and machines who make them. And we have, as last campus, the high-tech campus. That's all, small companies. And my field is biomedical image analysis. If you want to see a little bit more about my field, what I did, I have a website, Romeny, that's my name, .info. So you can check a little bit what I did, but that's not for the course right now. One of the famous things that we have done is scientific visualizations. We could visualize for the first time 4D, so X, Y, Z time. That's 25 images, 3D, 512 to the 3rd MRI per second, together with Philips, and we did the visualization, and we could show the vortices in the aorta. You see the blood flow here. This is a particle. And we did all kinds of experiments. We also did brain connectivity. You can measure the particle movement of water with an MRI scan. And water is, bumping around. It's called diffusion. And if water is in a nerve fiber, it can only move along the nerve fiber, not so much in the other direction. So if you study this for a while, you see a kind of an ellipsoid of the water molecules. And the longest axis of that ellipsoid is the direction of the fiber. Well, you do this in millions of fibers, and you connect them, and then you can make the visualization of the wires in the brain. So we did a lot of brain studies, and in the final hour, I'm going to go deep in what visual perception has discovered. That's just a revolution as we have in deep learning. All these computer science, the brain researchers, they discover a lot. What have they discovered in the retinal connectome? What is the retina doing? What happens in the thalamus? What happens in your visual cortex? So I'm going to lift a little bit of the most recent information of visual perception and how it is related to deep learning, of course. We use this connectivity in the brain to help neurosurgeons. If you remove a part of the brain, this was for epilepsy, you may come very close to the wires that go to the visual system. The visual system is in the back of your head. A quarter of your brain is for vision. You won't believe it. We are very visual machines. So all this deep learning from your brain is in the back of your head. Well, to prevent them to cut the optic fibers, we made visualizations, and now they could safely operate if it was in this region. Okay, one of my few last slides. If you go to classical computer vision, it's more or less feature detection. You do some pre-processing. It's the famous pipeline. And pre-processing is denoising, checking the color channels, etc. You do the first segmentation, and then you can do a lot of extraction of features. This is actually what happens in the first layer of deep learning. We have all these line and edge detectors. But before, we did this all by hand. Now we learn them. I'm going to show you what is the relation between these two. And you had famous families, as they call, Gabor filters, Tamura, locally binary patterns, you name it. And these features were then not only extracted, but you store them. And then there were all kinds of classifiers, classical ones, support vector machines, you name it, lots of classifiers. And what people did was more or less heuristic. Do a lot of classifiers, take 20, and we take the best. But how it works, we don't know. It depends on the data, they say. Well, some are Gaussian distributed, some have Poisson distributions, some have more, I don't know, high frequencies. So there's a lot of from the data. And I go a little bit deeper in some mathematics, what is the background of all of this? And then the classifier made it in this classifier, it's called a feature space. So you could say I have a blue feature space here and a red, and this is red is sick and this is healthy. So that's and the classifier is just the division line. You could go the simplest, that's a plane division, or you could have a quadratic division or some curved division. And if it's really curved, you have overfitting. All these things we can have a look at. And how good is it? That's called the receiver operating curve. The more it is to the upper left, the better it is. And people take the area under the curve, so that's a measure for how good it is. I go talk a lot about the relation between deep learning, deep because we have all these deep layers, and human vision that have exactly the same deep layers. So if to the right is the retina, you have here the first layer in the visual cortex, that's called V1, and then you have V2, V3, V4, V5, etc. And there are about 15 layers in the visual cortex that are really discriminable. You can see them. You can stick a needle in them, and you can see what they see. So you can check the filters of all these layers in V1 and V2. And you will see that V1 has exactly the same layers, the same filters as we see in these layers here. You see the hidden layer 1, very simple filters. So these are called edge detection, line detection, contour detection. And V1 has in the brain exactly the same filters at all orientations, at different scales, different sizes. And if you combine those, so you have these small line detectors and you want to detect some more complex groups, like a nose, you need 3 lines, they form a triangle. And that grouping in vision is called perceptual grouping. How does it work, this perceptual grouping? So we have a higher context here. So we really go see what is the mathematics of context to understand what these filters actually do and how they learn. And we will also see what is the most concise representation. Why do we need principal component analysis to make it as densely represented as possible? Because that's what the brain does. The brain has only one main goal: use as little energy as possible. So it must be extremely efficiently organized. And that's exactly what happens. Did you know, by the way, that your brain, that has 10 to the 10th of cells, only uses 25 watts? Is that amazing? We have all these megawatts of all these data centers and computers and so on, and your brain is only using 25 watts. So we still can learn a lot. And I'm going to point out a few areas where we can learn a couple of those things. So we're going to study hierarchical learning, and hierarchical is nothing else than from simple to more complex, to very complex. So you call it edges, combinations of edges, object models. Is by this way the screen, see, that's good enough? It's big enough? Okay. So our very simplest model at the lowest level is synapses. And in the brain, a synapse is nothing else than one connection of a neuron on another neuron. And this is a small electrochemical connection, and it has a weight. And that's exactly what we measure here. All these different weights, they are summed together. They go to a threshold, and this is the formula we normally have. So we're adding weights to a cell. And in biology, we have these neurons. And if a brain changes the weight, because it learns, it just swells the neuron. They become bigger. So you learn by making your synapses bigger. And if you forget, they shrink. And if they disappear, you have forgotten forever. So this same thing, and this swelling can happen in a millisecond. So you have a very continuous swelling, and some go slower, but that's actually the biology. And we used to have 3 layers that didn't work at all, and then we got these many layers. And this is the famous example that you all have studied. It is the AlexNet. And you see that you take very tiny images, in this case of digits. That's the famous MNIST data set. Who has never heard of MNIST? Okay, just very few. Let me tell you, there's a toy example that's extremely famous. And you see that 90% of the room has heard about it. And it's nice that you also learn about it. The toy set is 60,000 handwritten images of 26 by 26, of 28 by 28 pixels. And that's made available. And because it's so small, it fits on every laptop. You download it, and you can do digit recognition. So you make 10 classes from 0 to 9, and you design a very simple network. The network has just 7 layers, and that's the famous MNIST data set. I don't know what MNIST means, but it's something with digits. And when you train this, it really works. It's quite nice. And that toy example, there are quite a few toy examples. And we will see quite a few of them. And then you can train it with these small digits. But today, of course, we train with huge data sets. You all use Google Lens. That's quite impressive. And if you don't, download Google Lens, and you can point to any object, and it is recognized. They have 1 billion objects that are recognized, so 1 billion classifier. That's quite impressive. And they learn from Google Photos. You store all your photos on Google Photos because it's for free. Well, you never get something for free. Google learns from your photos. And there's an upload of 10 billion photos per day. So they have a lot. That's interesting. So we go study in detail what happens here because, as I said, we go to first principles. And we go to see convolution, Rayleigh max pooling, convolution again. And we're going to study backpropagation, error backpropagation, and why is that backwards. So a little bit about the philosophy. We go look at context. And to the left you see this is a catheter in a chest X-ray. And chest X-rays are always as bad as possible because you want to give as little radiation as possible. You can make beautiful pictures, but you kill the patient. So you must be very careful with radiation because it induces cancer. So they're always noisy and speckle and yeah, can you see something here? This is what you see. So if you do a local analysis and you look at a small area, you don't see anything at all. But if I show you the rest of the image, now you see what was invisible here. This gives full information about something much bigger, and now you see it. So contextual processing is actually the big thing we are after. And what is deep learning doing? It's nothing doing than contextual processing. It really takes into account a much bigger context. And the deeper you go, the context gets bigger. So that's actually how can we understand how that works. So it is much more than just statistics, etc., etc. But what is this perceptual grouping doing? And people have thought in psychology a lot about perceptual grouping. What makes it that things are combined? The famous Gestalt laws. You see 3 horizontal lines here. It's called proximity. Well, not lines, but they are grouped in some sense. You don't see vertical ones. So some closeness must be in some way involved. So we're going to look at some Gaussian radial distance. Similarity. So we're going to build a tensor in which we can see, well, how much is the same? Do they have the same color, the same intensity, the same orientation? You name it. Are they enclosed? Do they have symmetry? You see typically which brackets belong together. Here, we easily close it. You see, this must be a circle and something is in front of it. We call it occlusion. We're extremely good in handling occlusion. I see most of you partly because someone else is sitting in front of it. But I have no problem with identifying you as a person only if I see a quarter of your head. I fill in my brain the rest because I saw that before. And that filling in happens in level 6, level 6, level 7, level 8. There they know the whole structure, and you only need to see a part of it, and you get that from the earlier levels. So that's a little bit the main philosophy. I already told you that we only use 25 watt, and there's another interesting thing. These neurons, they only fire at 226 kilohertz. That's extremely slow. This laptop is 3 gigahertz. That's 3 billion hertz. So if I can do the same as the brain, which does it at a few kilohertz, that's 1,000,000 times faster. So if I discover how the brain is working, actually, and I can use, instead of kilohertz, I can use these gigahertz, I can make extremely powerful machines. And we aren't there yet. We think that deep learning is fantastic, but it is very, very much in its infancy. We still have a factor about 10 to the 9th or so to go. That's not 10%. That's not 100%. That's an incredible amount. So we still have a lot to learn. And that's you, the next generation, to work on. And I'm going to show you that the retina is not a regular camera. The retina is actually a tensor measuring machine. It measures, you have 26 retinas. Did you know that? You don't have just rods of cones that give the signal back together, but there are 26 different tilings, and one measures orientation of velocity in one direction. One measures relations to each other. One measures in a small circle, is there a singularity? So it's not a camera, it is a perceptual grouping preparator. So it really works to send you a very complex image. You know that in the first layer of deep learning, you have these, in MNIST, you get these filters, but you have many filters. You have filters that measure in different orientation, etc. Well, these filters exist already in the retina. Most people don't know. We're going to look at some neurophysiology, how that field is understood. I spent most of my career with doctors, and they needed to see, can you find the tumor or the narrowing of the blood vessel or whatever in medical images? We have so many medical images. We want to automatically find the tumor in the chest X-ray. And I said, well, there's one big recognizing machine that's really super, that's the brain. So with my group, we quite intensively studied the brain. So our group was quite well known for brain-inspired computing. And the deep learning comes now really together. So if you see the brain, it's quite complex. You see that from the eye, it goes to the center, and then there's a big radiation going to all these layers in the brain. And if you see a layer, this is the brain. If you cut it, there are 7 layers in the brain, and all these layers do something. We're going to look a little bit what that does. Okay, so I go talk about Mathematica, and everybody is programming in Python, because that's the main language of all. So why should you work in Mathematica? Because it costs money. And people think it costs a lot of money. And I will show you that it's actually not costing a lot of money. I made what you call a word cloud, and there's a huge tower of Babylonic languages. There are so many languages, COBOL, Perl, SQL, Java, etc. And sometimes you have to choose which language shall I choose. I took Mathematica because it can speak mathematics. It can really do mathematics as you like it. It can speak English. It is the most English-like language. It is very much English that you program. Because this command line interface that you see here is actually pretty much from the 80s, from the 90s. It's extremely old-fashioned. You cannot type a pi. You cannot type a square root. Yeah, you can type \sqrt and like in LaTeX, etc. That's very old-fashioned. And Mathematica is already around for 25 years, and my whole life I programmed only in Mathematica. It may be strange, and I'm a little bit amazed that people have not looked at it because it costs money. So everybody does it, uses Python. And if you really look how much it costs, almost every university has a campus license. My university has a campus license. And we have 10,000 students, and all these students get a laptop for free in the first year. Mathematica is installed for free. I have never paid anything for Mathematica because my university had it. And I think if you check, your university has it, and you download it for free. If you want to buy it as a student, it costs 99 euros a year. If I see what I pay for a car, what I pay for anything that I want quality, yeah, you pay a little bit. And this is so little money that I'm actually very surprised. But I go show you a little bit how it works, because you have never seen it. And if you are a professor or something, you could say, I use the home version, it's 213 euros a year. And people think it is 5,000 a year or 10,000 a year. They think. But if you look, it's actually very cheap. I have the websites here, and I go a little bit talk about what we do in this course. We program in a high-level language, and all the code that I give you is available. You can download a free version of Mathematica for 2 weeks, so if you want to play with it, just play with it. If you don't, you can all forget it and just see, I had an interesting couple of hours, I just saw it. It's fine. I'm not a representative for it. I only say that the speed of working was so incredibly increased, not the speed of processing. It's about the same as Python, because underwater it's all C++. But directly, if I get a paper, within an hour I have the code. And that's the speed. So, the first hour I give you some classical things. So we're going to look at how do you program a network, how do you make these layers, etc. And in the second hour, we build some applications and some nice visualizations. I'm going to use my camera, and I show you what happens in layer 1, in layer 2, in layer 3. We're going to really see what does these layers inside, what do they do. Hour 3, if I be right in time, I'll tell a little bit more about what's the deep insight in backpropagation. And hour 4, then we go really into the very interesting first principles. How can we get the mathematics of self-organization? How does that work? So I must warn you, we go do a little bit of mathematics in this course. If you hate mathematics, take the other courses, there is enough. But if you really want to understand some deeper intuitive feeling, and I will explain everything intuitively. Hour 5 is, I show you that all these geometric deep learning things are actually geometric engines. So these line and edge detectors are no line and edge detectors. They are differential operators. So we look at derivatives of images. An edge is nothing else than the first derivative. Curvature of a line is the second derivative. And we need all these derivatives to describe structure. And that's what I go teach you. That is one of the first principles. And they automatically emerge by learning from patches, etc., how they do. And the last, I go to the visual system. You can take a picture of this page. I made a special web page for this course, and everything is there. The PDFs of everything I show. If you don't have Mathematica, you cannot download it. Mathematica is the biggest program ever written. It is more than 5 gigabytes, and there are no packages to download in Mathematica because everything is included. So you never have to search for anything. This is the password and the user. So if you go to this website, it should open. Yeah, you see here a little bit, and it's all explained, and you see here download all the PDFs and download all the notebooks. So it's, for those who want to see it, check it out. And here you see a description of all the lectures with pictures, and if you have no time, and I have not enough time to discuss it, afterwards you can, just at your own pace, look at all these things. So I did a lot of work in, and have some recommended reading. This is an outstanding book on machine learning, but it's fully written in Mathematica. This whole book is written in Mathematica, and the full code is available, downloadable for free. So it's nice. Okay, let's get started. My last slide is, yeah. Are there any questions so far?
Can we see the user and password?
Yep. Make it bigger. Any other questions? Not yet? Okay, I go speed up a little bit because we are running out of time.
One question.
Yeah.
Does it also work with the online version of Mathematica?
That's exactly the same.
Okay, because that's not, then you don't have to download 5 gigabytes.
No, but I can very much recommend, because sending things back and forth over cloud, that takes so much time that you get really bored.
Okay, yeah.
It works, it's fine, but then you have a data set of several megabytes,
Yeah.
send it up, send it down. It's a little bit, it is nice, but it works far better having it locally. Then you have an SSD,
Yeah.
multiple processors, you name it. You have your GPU. It works incredibly much better.
Okay, thank you.
I give a summer school in September. This is the biggest summer school in Eastern Europe, very much like this, same size, but we have very sophisticated speakers from Google, Technion. I'm in the board of this already for 5 years, so if you want to have this again later in September, have a look. I'll put it on my website as well, 5 to 9 September. Okay, I close all this. I start the first notebook. Now I start Mathematica. Let's see. Is this big enough? Can you see the code? Because I can easily change the size of the screen, but is this about fine?
Yeah.
Okay. Mathematica is a notebook, and recently they have discovered notebooks again, but Mathematica works already for 25 years with notebooks. So this Jupyter notebook looks like a nice invention, but it was all copied from Mathematica. It works with cells, and you have a cell here, and this is a cell, this is cell 2, and this is a cell group. And you can close the cell group by just clicking on it, and then you can open and close and really nicely work. And here on the upper left, you see that this is a subsection. We go look at multi-layer perceptrons. And something are a little bit different in Mathematica. You have to learn it. Everything is a function. So, and the function is with square brackets. Round brackets are for just grouping, and curled brackets are lists. So sets, series. So this means I have a net chain, that's nothing else than a chain of things. And this is the function, you see the function here, and by green you see immediately the pairing bracket. So net chain is a chain of a net. And this means it is a little group. So this is a little group that has first a linear layer, then it has a ramp, that is the ReLU. So it has 0 for negative values, and it has just identity for positive values. I have another linear layer, another ramp, another linear layer, and then I have a softmax layer. The softmax layer means that I have kind of values, but I want the values make such a way that they add up to 1, so they become probabilities. And probabilities always have, you cannot have a probability higher than 1, so they add up to 1. It's a simple formula that's implemented in this layer. And then you say, how is this network actually working? Because you see very few parameters. The input is a set of 2. so that it's just a vector with two numbers. So if you make this multi-layer perceptron, we call it MLP. I now run it, and the first time it has to load the kernel, so it takes a couple of seconds extra. I get a nice net chain connected. It is not initialized, so the weights have no value yet, but I can have a look at it. I just check on this plane, and I see, okay, here is the input, the linear layer, and it's red because it is not initialized yet. So the vector, the size of the input is vector 2, and then the linear layer makes it size 4. So the output of linear layer you have to specify. The input it knows by itself, because you gave it. If you specify here layer 14, it gives you 14 as output. If you click on this input, you get more information. You see it is this, and this linear layer, you see you get all the parameters that you click on. So everything is mouse sensitive. And you see the output dimensions is 4, it's a matrix, 4 by 2, etc. So this is quite nice. This is the softmax layer. You can look at the output. Now we do net initialize. And there's another lesson. All the factory functions are with capitals. And there is no abbreviation. There is no silly naming. And Pythons, I see some names that I really, how do you get a name like this? How can I ever find it? Well, if you want to find the function initialize the net, okay, it's called net initialize. It's not so difficult to learn, actually, because sometimes a function is really long, but it is exactly the name what you want. Principal component, you name it. So now I initialize the net, and now I get the same net, and now you see it is not red anymore because it is nicely initialized. If I want to see the graph, it makes the net graph, and now I have it in a more graphic function. So here you see the linear layer. What is actually a linear layer? It's called a fully connected layer. It's nothing else than a not square matrix. So it has, let's say, 5 by 7 elements. And you go from a vector from size 5 to size 7. So a linear layer is nothing else than a size changer. So you go from size 14 to size 1000, or you go from 1000 to 2. If you have a matrix multiplication, you see that your vector changes in another vector. You need a lot of coefficients, that's the whole matrix full, but we learn these coefficients. Well, this is, of course, the ramp, so you click on it and you see this is the ramp. It's an element-wise layer because it does point by point exactly this ramp. And it is so here that circles do a fixed operation, and these squares, they are learnable. So we're going to train this net, and then we learn one by minimizing the error. So if I put now, it has learned something, I put a vector in there, so I have my MLP, that's my network. It's now a function, and I can put something in the function. A function is nothing else than a small machine, and it has a slot. You put something in, you get something out. If your function is square it, you put in 3, and you get out 9. Well, here I put in 1.2, and you see it is between curly brackets because it is a list. What do I get? Everybody can predict what I get. I get, let's click on the output, a vector of size 4, because that's what all my linear layers said. So if I put in any vector of 1.2, I get these 4 random numbers. If I put another vector in, I put, I don't know, and this is so nice, you can work interactively, you get another one. So playing with it, it's an interpreter. You can just go back, change your values, look at it. And now we go train it. So if you train a net, it's called net train. And suppose we only train a linear layer, we have to specify the training examples. Well, and this means 1.5 has to be trained to 0.8. And this is the classical pair that you give to a network. MNIST, you give, okay, this 28 by 28 small image is a 6. This 28 by 28 thing is a 5. It's called key value pairs. So the key is 1.5 and the value is 1.8. And this could also be images. This could be vectors. This could be anything. This could be electronic patient records. You name it. It's now very simple things. And how do I want to check the performance? Give me a loss plot. So now it is training this network. And you see it is now doing all these iterations. And you have nothing else to do than say net train. And it shows you interactively the loss function as a function over time. Let's see a little bit more complex network. This is a chain of layers. You see linear layer, ramp linear layer. And this is called another net chain. So I have a net graph here. It's quite small. But you can make it very complex in Mathematica by just saying, I put a bunch of layers. So this is linear layer with output 10, no matter what I put in. Then a ramp, another linear layer. Catenate layer means combine them. Summation layer is add them all up. And there are about 20 of these layers, and you can quickly see what are these different of layers. And you just give them names. So this is layer 1, this is layer 2, layer 3, layer 4, layer 5. And then you say, okay, I need to connect the output of 1 to 2, the output of 2 to 3, etc. And the input is 3. This, by the way, means apply that function. So it is the same as put net initialize bracket open in front of it. But you can also say, if you forget, I want to do it postfix, I want to do it afterwards. So I can say, I want to have the numerical value of pi. And now you see you can nicely write the pi. You get the numerical value of pi. And if you want to say, I want to have 1 million digits of pi, let's say 1 million, it takes a while, but now you get 1 million digits of pi. And it's really 1 million digits. It's, let's forget about it, but if you, I was talking about, if you say, I want to have this numeric, let's forget about these digits. So if I have, I type pi, and now I say, give me the function, and this is exactly the same. Now you get pi again. Okay, I delete this cell. But now I want to make some complex layer. This is just an example. I'm not going to explain what this network does. It's a silly example. But it is the way that in a one-liner, I can now make pretty complex networks. And this is a network. You see, okay, I have an input here. And this input is, let's click, vector size 3. Then a linear layer that gives me this one. Then a ramp. And you see that 2 is connected to 3, so that's this one. And the numbers that I give here make automatically my topology. And now in a one-liner, I can make incredibly nice networks with branches. If you want to make a UNet, you want to make a ResNet, it's just in one line. It's very convenient. And you click on any box, and you get exactly what it is. So here you see this is the catenate layer, and it is connected. And the interaction that I immediately can check, is it right? What does it do? I click on it, how much goes in, how much goes out? That's what I really like. And that's what makes it programming quite fast. This is a luxury program, I might say, but it is designed by an incredibly big group of people, 400 mathematicians. There are millions of users actually, mostly in the mathematics and physics world. And yeah, I think it's time that deep learning discovers a little bit of it. If you really have a function, this is quite complex, and maybe I can only display it when you have learned a little bit more, and after a couple of hours you feel more confident, because you need to learn the language by doing it. Seeing this is, hey, for the first time you learn some, I don't know, Finnish or Japanese, it's completely not understandable. But here I have a function layer, and that's a mathematical function. let's first show you what it does. A function, well, actually, I skipped this. It is a little bit too complex for what I show you, but this is the function that is actually made. This function layer is automatically telling you that it's a subroutine, and it has x, y, and weights as local variables, so not known outside the subroutine. And it has input foo and input bar, and there's a dot product between these two. And I call that x. And then I have y, that's the square of x. And then I have weights, and that's nothing else than a small array of just two numbers. And now you see what the thing does. This dot layer is automatically made by this function layer because it recognizes here a dot. The square root is also recognized, and this function is taking the square root. It adds them all up here. So whatever function you put in here, if I put x to the 16th, it makes an automatic layer that programs the whole thing, take it to the power of 16. And if I take whatever complex function here, take exponents, whatever, signed functions, it creates the networks that belongs to it. And that's very, very nice. If you go to a level that you build these networks and you want to make some complex constructions, we're not yet that, but it's just to indicate it's a one-liner. It's very easy to do. Okay, now let's build a very small network with mushroom recognition. Okay, I have 4 types of mushrooms, and I have them here. This is called morel, bolete, parasol, and I'm going to read these images from Google Images. So I asked Mathematica, do a web image search. And this is an interesting thing that's called hash. That's the way that Mathematica works with functions. Let me show you this here. This is a function, f. And what does this function? Take something that is gone into my slot, raise it to the 3rd power, and take the sign and add them up. So this is the slot to the 3rd, and sign is 6. Sign. That's what the function really has to do. You can put anything in there. And if I put this at the end, that means it's a function. That's all. So now if I do f on something that I call AA, that's my variable, well, what do I get? AA to the 3rd plus the sign of AA, of course. But sometimes people get confused and say, hey, I see this very strange thing. It's nothing else. It is a function. So there must be some hash signs in before that says function on what then? And if I have many hash signs, it's hash 1, hash 2, hash 3. You can make as many hashes as you want. So now I do a web image search. And this is another thing, and then I have mostly got it. This means map. Do it on all. Classes is a group of 4. You see, 4 strings. So do this function first on morel, then on bolete. It's very simple. So this means this function, do it on all elements. A map is fantastic because you don't have to do any, how many, there's no for loop, of course. Of course, map is a for loop inside. And of course, everything is programmed in C++, so there it is a for loop. But for loops do not exist in Mathematica anymore. You just want to say, as you say it in English, do this on every element. And that's map. Then we make images, we put them on an automatic scale. We take a seed from random, and then we take a random sample from all these images. In the meantime, we now go do it. And Mathematica is starting now this web image search. I hope the network is fast enough. And you see it is very small code. I should have started this and then in the meantime explain it. It's now downloading the images. Oops, it goes a little bit slow. Oh, I have it here exported because it goes so slow. And that's due to the network, I think. But otherwise, it is just downloading these Google web pages. It takes the images from these web pages, and that's all. So let's stop this one, and let's read the data set itself that I have on my thing. So let's check if everything is all right. I take a random choice from this data set, and you begin to understand the way Mathematica is figuring out. You see, random choice with a capital, square brackets, from the data set, how many? 5. So the syntax is extremely simple, and no abbreviations. And now you see the key value pairs. This image is a bolete. And what is so nice, you directly see the image. You can put these images as variables, because everything is symbolic. If I want to take this image and use it in a square root or whatever, you can put it in a square root. And then it takes the square root of every pixel. So it is very as you like it. If I want to put another image here, I can drag it from a window, another window from a web page, and drag it into my code. Well, that's very convenient. Okay, so I have here 5 examples. There's a function dataset with a capital, and that puts it in a really nice order. So now we can check the dataset. And this function is designed to work with millions of data. So it has a scroll bar, so you can just scroll it down and see all the key value pairs. So let's see, we have now all these mushrooms here. And now we go make a training set, a validation set, and a test set. So we take from the list, and what is the list? That is data set. We take 100, 50, and 50, and we add them to these things. So you quickly see what belongs to what. So this is not 3 lines, it's just in a single line, you add them to those. Now we're going to use networks that already exist. And there's a very nice website, and it's called the Wolfram Network Repository, the neural net repository. And all the famous networks that exist, you can download there, hundreds. So if you want to have the famous net, and you see all the networks here. Inception v1, LUNet, MobileNet, Inception v3, and all of them you download the full network in Mathematica code, and you have the construction notebook, you have everything. It's really nice. It's extremely nice, actually. And they're fully trained. And they're fully trained with the ImageNet network for free. So you have all these networks, and they're optimized for speed, and they run on your GPU, etc. So it's really nice. If you work with natural language processing, all the networks are there. You're specialized in UNets for segmentation, or you want, I don't know what. And you call them by the name. So if I go to my Mathematica code again, and now I import a net model. So here we're going to import in the next line, this one, the net model with that name. And it is not just not an abbreviated name, this is the full real name. If you don't know the name, you just give net model without an argument, and now it reads the web page, and it tells you exactly what are all the networks available there. I'm a little bit afraid that internet is slow, but now you see it read from this web page. So the web page is continuously updated, but now you get the latest update, and you just say, okay, I want to have this one. Okay, copy the title and read it. I remove this line. Okay, so let's read this net model and see what happens. It read the whole net model, and now you see, what is it for kind of net? Okay, it's quite a big net, and it has all kinds of blocks. That's called a net graph, and this is a net chain, so it's actually quite nice. This has 9 nodes, 11 nodes, and if you see how big it is quite a big network. It doesn't even fit here. If you see the net not as a chain, but I put the function normal in front of it, and this @ sign is the same as the square brackets.
Can you scroll to the right in that visualization of the net?
That's exactly what I could do, but then I have to show it as a graph. And now you see all the key value pairs that it is made for this network. This is the first convolution layer, And of course, you can click on this layer and see what's in there. It's exactly that. And for every layer, you can see that. But it has the name stem_conf. So I can call the network under that name and do something with it. Take it out. We're going to do network surgery. So we take a layer out and we put in layers in. So we can take some trained layers from another net, etc. So this is now quite a big network. If I take from the network the last 8 layers, well, what should it be? Net take. From which one? From the net, and -8 take it from the end. If I take +8, it's from the front. So now I take the last layers at the end. Okay, I get the last layers at the end, and now you see I get from block 7a to the output. So it's very simple to cut and paste, etc. layers. You can see it, you can click on it. It's actually so convenient that I don't understand that people haven't discovered it yet. But let's see. The speaker after me talks also about networks in. But okay, I'm at the very beginning of 6 hours of this, and you will see many more surprises. Okay, the last one, it's called predictions, gives a vector of this one. It gives a vector of size 1000. Well, we want this to be 4, because we're going to use this network in our mushroom classification. And we had only 4 mushroom types, so we want to change this into 4. So we first replace the output by a decoder that generates 4 classes instead of 1000. And you all know what is an encoder and a decoder? Encoder means it goes in. So that means what goes into your network. If I have images, well, a network doesn't understand images. You have to make this into a matrix, into a vector. And you have to specify what it is exactly. So the encoder makes it suitable to go as numbers into your image. Suppose you have some electronic records, or you have some classes, male or female. Yeah, that's not a number yet. You have to give it a 0 or 1 or 1 or 2 or whatever. That's the encoder doing. And the decoder does the opposite. It takes the numbers from the network and puts it in something you want. Could be a number, could be a class, could be male, female, you name it. So what I just say here, do a net replace part. So I replace a part of my network. That's what it's all called net. I do this in the network net. And I replace output by a new net decoder. And that works on classes. And for the predictions, I use a linear layer. And I do not specify linear layer here because the output knows, because this guy is length 4, classes has length 4, it knows that the output is of length 4. So that means the linear layer just in front of it knows the output has to be 4. So I really don't have to specify it. And Mathematica is extremely good in what's called inference, knowing from the network. It knows so much that you don't have to specify linear layer. It does it for you. It knows it has to output, it gets something in, 4 numbers. So that's why I give it here 0. So I call it new net. And now this new net is right here. It is the full original network. But one thing has changed. I have a new linear layer here. It's called predictions. And this linear layer doesn't know anything yet. It is not trained, so it is red. And I have then the software layer, but you see it's output size 4. And then I have an output that gives me a class, which mushroom is it? And that's all the same from the network. So I have now done some network surgery. So if I now take this network and show it as a graph, so that means take from the network, new net, the last 8 layers. This means a function, show it as a graph. I have them here, and you see I have them now here, and this guy is red because it is not trained yet. So now we go train the network. Let's train it. We use the function netTrain. On new net, that is my net after the surgery, what do I use as a training set? That was called training. You remember all the digits? I had 100 in the training, 50 in the validation, and 50 in the test set. I want to see all the if you don't know how NetTrain works, you put your mouse on it and you get a small eye here. You click on the eye and then the documentation opens. And this is the world's best documentation that has ever been built. It is about 16 million pages of everything, of mathematics, of linear algebra, of whatever. And everything is a Mathematica notebook. So if you see NetTrain, what does it need? A network, and then how the inputs and outputs are connected. You can also give it more data. You can give it a specific data set. Well, there are many ways. This is how it exactly works. You can set all kinds of variables. I have now a very complex one here. It's pretty amazing what you can do. And then you get examples. This is a very simple example. And you see it is a cell. You can say copy and put it in your notebook. Well, what is easier than that? It is full working code that you can use. Okay, this all means I want to see all the outputs. I have to be a little bit careful on time. As a validation set, I use my 50 validation images. And as learning rate multipliers, that's important. All my learning rate multipliers are going to 0. And this means any. The underscore is a pattern matching thing. It's not easy to understand, but it means anything you can think of. It is, if you, I come to more examples of this one, but this means all of them go to 0, but the one for the layer predictions, the multiplier go to 1. That means all the layers are not learning, because they have a learning rate multiplier by 0. That means do not update them in my iteration process. Do not change the value. But the prediction layer, yes, you should do that. And you should fully let them learn. And you make a learning rate multiplier by 1. If you let it learn a little bit, you make it 0.5. But we want to have it just plain full learning. And my target device is here the GPU. So I'm not going to train it on the CPU, but on the GPU. Let's see what happens. It is now automatically taking my network, put it on my GPU. I have a very nice GPU here. It takes some time to get everything done, but this is so nice. I don't have to do anything. Mathematica is taking fully care of the whole training and doing things. It should go a little faster. Not sure if I forgot something. If I forgot something, okay, it works. It took some time to prepare everything for the GPU. And now it is learning. And you see very nicely that it gives me, oh, in this case the error rate is a little bit spiky, but it works. And learning, it works. It really learns, and it gives you some specific number. Take the Adam optimizer, batch size of 4, working on a GPU. And you see a scroll bar here. And you just wait until it's finished. And now we have the result. And you see, okay, that's quite nice. We have a loss here of 6%. And this is extremely convenient. You just say target device. You can say target device, if you don't know, it's a string, so you could say this string, and then it automatically gives you always your options. And in this case, it's very simple. It could be a CPU or a GPU. Well, in this case, we want the GPU. Okay, I did it wrong. If you, for the first time, download Mathematica, and you don't have your GPU installed yet, yes?
Is the batch size calculated, or
in this case, it is taken the default values. It automatically says how big is the data, what is expected, and then it takes a heuristic number that's optimized for that. But of course, you can specify everything. The batch size, no matter how many cycles you want, how many epochs, everything is programmable. And if you don't specify it, it takes what people normally do. if you want to install everything for CUDA, you just check CUDA link, and now it is checking my full computer, and it says, if you need something, you don't have CUDA libraries and compilers installed, oh help, how should I do this? Then normally you go to a website and you download the latest CUDA version, and then it isn't compatible because I have Python so much, and all of this is gone. It's done fully automatically for you. It downloads the latest libraries, it tells you downloading this, downloading that, installing that, and then it's done. And then at the end you can just specify, it's all right, you type CUDA information, it's checking now my full computer, and it tells me everything, okay, this is my full CUDA thing. I have a core count of 920, so I have 920 counts of cores in my GPU here. I have 8 CPU. It's a big computer. It's really nice. But that makes it convenient to work with. The clock rates, and this is convenient because you really want to have it. If you want, for example, the system information, you see you can you see system information, and now I do this. Now it reads my whole computer and it reads everything. So how many GPU kernels do I have, etc. And here is coming what my computer looks like. And it's convenient for you to do this once. Here, for example, you can check parallel. You see I have 8 processors. Yeah, how many kernels can I run? How many devices are connected? Do I have DirectX, OpenGL? How is my network? How is my machine configured? It's very professional. I cannot tell you how incredibly professional this is. And it's so easy, you can directly access whatever you like. Okay, that system information is not so useful. Okay, we go see, is the network really working? So we look at the trained net, and we extract from this trained net the trained net, because it was results, and results is everything. That's a trained network, that is the, yeah, all the, how can I say, all the measures that give me how well it worked, so it is the, anyway, I extract the trained net, and here is my trained net, and you see the linear layer is now no longer red, and let's now test it on some images, and this is the way you do this. You put images in there, and let's see what it is saying. Okay, the first one is a Belete, a Morel. It works. And that's actually quite nice. And if you want to see the things that you can extract from results, because results is a big group of things, you can extract what properties are available. And from this trained network, you can extract the loss plot, everything, the net, you name it. It's incredibly versatile. It goes far too much for the little time we have now to show you, but I just want to show you the things here. And if you want to check the network performance, you just say, well, what are the classifier measurements? It is processing now these data, and here are all the measurements. You see we have the matrix of the input and the output, all the numbers, and given time, I do not explain this in full detail, but you can have the confusion matrix, etc. Okay, enough about this. You want a small break, or shall I continue? I have another 40 minutes left. Shall I just go on? Or is it 2 minutes break? No, let's go on. If I go too fast, or you say it's too much code, I want to see more images, I can easily change things. Yes?
I had a question about the transfer learning.
Yes.
Why did you add a layer and not change the layer? Because that's already compressing for another data set.
I do not understand the question.
So you added a layer?
No,
on top of that?
I replaced the layer.
Oh, you did replace. Oh, okay. Then I didn't pay attention.
it's always plain English what you do. Let's go back to that where I did it. This was the whole network. You say, I said, where's my mouse? Here, replace.
Yes.
And because it's always plain English, you are never confused what is the function actually doing. This net replace layer takes a network and it replaces a layer. It cannot be more English. Of course, it is condensed, but it's actually very nice. If you look for a function, you say, hey, well, what should that function be? I don't know. You have, for example, a list of 1, 3, 4, 5, 5, 6, says, and now you say, I want to count the 5s in this list. You say, okay, count in this list the numbers of 5. You see? What you want is the function. No for loops anymore. You just say, what is the position of the 5s? You get the position of the 5s. It says it is at position, in this case, 5 and 6. So that's called functional programming. And function means what you like it to do, that's what is your function. Okay, let's go to transfer learning. Last thing.
Maybe I have a quick question about the inputs.
Yes.
Because what we very efficiently and easily downloaded them before, but they also seem to have different sizes. Like, is that part of the efficient pipeline that they are sort of cropped or adjusted to the corresponding input size, or is that where is that part happening?
It happens in the encoder. So the encoder says, well, this network expects images of 222 by 222 pixels, etc. But Mathematica is quite big. I'm going to show you some COVID DNA analysis, where we have 16 gigabytes of data sets, millions and millions of DNA strings, and it can handle it fully on this laptop. It doesn't matter what size you use. It just depends on your hardware. If you have a small computer and you have a big data set, yeah, it will never work. But in that sense, it's exactly the same as all the other languages. And it is fast. People think Mathematica is slow, but it's not.
I'm actually not talking about Mathematica, but about the network itself. Where does the part where you adjust the variable input size or the variable sizes of the images, where you adjust it to the input that's expected by the layers? That's happening in the pipeline of?
Yes, it happens in the pipeline, and you just see this is input. I took this net from the already available trained nets. You remember?
Yeah.
Well, there it is specified. And they said, well, we expect a 3 by 224 by 224. So this is a color image of 224 by 224. If you want to change it in your code. Replace the encoder by another encoder. And then you can read, I don't know, megapixel images, anything you like. Does that answer your question?
Yeah.
This was given because the network I used, that's a classical network, the original programmers, probably by Facebook or whatever, they put it in this way.
So
And
if you wanted to know whether it gets cropped or, let's say, zero padded or whatever, we have to look at the website and efficient nets code.
yeah, but you can, if you have the net downloaded, you can see exactly what it is. If you download this network and you put between brackets construction notebook, you see in great detail exactly what happens. Every step. And then you see, oh, there's a cropping, or there is a, you name it, padding of images, or padding of zeros, or it is cyclic, you name it. So if you are afraid of that there is no flexibility, there is incredible flexibility. Yes?
What if the images of the mushrooms that we have downloaded from the web have different sizes of tools?
Then the encoder makes it the same size. It just says resize. So if I have an image here, and suppose I want to do image resize, and if I don't know how this works, then you say, okay, I take image resize. You see, I take an image, and I need to specify the width. That's simple. So underwater, Mathematica does that. So I say I take image resize, and suppose I take this image, I copy it right in here, and I say I want to have this at 50 pixels. Okay, it makes it 50 pixels. If you want to make this interactive, you can just say, I want to manipulate this 50. I want to make it a variable. Well, you call it size. And then you can just say manipulate. Manipulate this image size. And now I say comma. And now I have to specify that its size goes from, let's say, 20 to 400 in steps of 1. And now it automatically creates a Java applet. It starts at 20. And now I can change the size as I like it. So everything you want, you can change it interactively by a one-liner. Isn't this cute? And if you want to see how much am I, then I say, okay, do it like this. I'm now at size 212. But if you put a formula in here, you can do mathematics. So if I have a manipulate, for example, I do some algebra. I have expand this function. Oh, sorry. Expand this function, let's say x plus y to the power of 2. And now I see I write to the power of 2. It is not had 2. That's from the 80s or 90s. That's from a long time ago. You never write this anymore. Or you can write, suppose you want to do this as a square root. You write it as a square root. You really write mathematics as it should be. And that's modern programming. And I have no idea why people are still working with this, character by character and line. That in Word and in all the other languages, I don't do this already for decades anymore. Anyway, let me just finish this. If I expand this, you get this. But if you make this, let's say, larger, you make this square root, you make that 5, you get a bigger one. And you see, it nicely does. And every mathematics you can imagine is in there, no matter how complex. And you can, of course, now easily see what I go do. If I say manipulate this function, and now I make this n. Sorry. I make this n, and now I say n goes from, I don't know, from 1 to 100 in steps of 1, because I cannot not have half. Now you can do interactive algebra. Isn't that nice? And it's fast. If I do this to 1,000,000, it does it to 1,000,000. Of course, I get some quite nice formulas, but it doesn't matter. But you see the notation, this is exactly how it is made for humans. Yeah, there are no small things. Okay, I want to speed up. We're going to do a trained network, and we begin with 16 mushroom examples, and I just give them the key value pairs. So this image is a Borlete. This image is a Morel. You see how visual the input is? It's exactly as you want. It tells you that this image is that. And what is so important to realize is that you are visual machines. A quarter of your brain is for visual. So everything should be visual. It should be images. If you see slides, then people have a lot of text. But take images. I've seen lectures that were about a new communication thing. And it was bullet after bullet. It was cheap to make, and it was fantastic, and it was hexagonal, and it was modern. And you had no idea what it was about. And then at the end, it was a picture of a pencil. And I said, why all this stuff? You could immediately see it, and here you see it. Okay, so I make this variable small data, all these images. I load a network, and this is a Wolfram identifier network. It's quite a big network. You see, lots of layers, and every layer I can study. This can distinguish about 4,000 objects. So let's see what it does. And it gives a mushroom. but that is not detailed enough yet. So we need to add more to this layer, that it knows the type of mushroom, that it is a bolete or any type. So let's make this network, it's quite a deep pipeline. As you see, it has lots of layers. If you want to show all the layers, I'm not going to explain this code, but now it breaks them apart and you can see them in a little bit more stylish way. And this is the whole network. Pretty complex, as you see. And I don't care about how complex it is. I just want to use it as a network that is trained before. And it has lots of knowledge in there. It was trained on, I don't know, millions of images. If you want to put it on your screen with a scroll bar, that was an earlier question before, you flatten it out. And now you show the net graph. Come on, it's a little bit big. And now you have here the whole network with a, come on, where's my mouse? And now you can scroll down. And still you can click on anything and you can see, what is this guy doing? You see? It's quite interactive. Now I'm going to take the first 22 layers and I use them as a feature extractor. So what is this first 22 layers doing? Well, this is the network. It takes the input, lots of layers, and at the end it spits out 1,000 numbers. So that's a feature vector. That's called the internal representation for what you put in there. You have all worked with those things. So it makes an input image into a feature vector. How am I doing with time? Yeah, what is the end of this lecture?
10 minutes.
Oh, you have to okay, 10. It's fine. If I take the output, so if I take this net 22, the first 22 layers net, and I put a mushroom in there, I get 1,000 images, 1,000 numbers. I display them as a short, so that means do not show them all. If I do not put short, I get them all. So here you see all these numbers they get out of this network. Okay, it's a lot, but don't worry. If you have all this stuff and you want to get rid of it, you just click on this layer and, oh, in this case here, you double click on this layer and they group together. Now I use this function classify, and that is an internal network, but I use as a feature detector the first 22 layers of that net. Isn't that cute? So you say, I have a network built in Mathematica, it's called classify, but I want to use the feature extractor that was trained by this famous network. And I can use any network, of course. I can use a famous ImageNet network or an image net that was trained on ages of faces or specific tumors or you name it. So now classify is building that in. You see, it takes a lot of work, and now I get this classifier network. Let's see how it does now. The name of this classifier is very simple. It's called C. So C is now a network. So let's do C on two images. You see, C is bracket open. This is the function C. It's a network. And what do I put in there? A list of these two images. And let's see. Now it recognizes it is a bolete or a morel because I use this much more fancy classifier in there. So that's called transfer laning. The message is, of course, I did this in 5 lines of programming. And that's why it's so fast. So once you get to learn this, you're incredibly efficient in doing these kind of things. If you want to see, let's load 50 more images from the web. So I do a web image search again. and I ask for Morels and Boletus. Unfortunately, I have a little bit, network is a little bit slow. That goes, anyway, it works quite nice. Yeah, that's sufficient to say, I have to do like this. Because it has to read after this another 50 images, and I have only 8 minutes left. I have to skip a little bit. What did classify do? That's the internal function. And of course, you always want to know, and classify is a very fancy function. Classify is the Mathematica version for AutoML. And what is AutoML? It's a very famous network by Google, and that is, yeah, if you don't know what network to use, just use a lot of networks. It does it automatically for you. Use a lot of training parameters, and do endless experiments, and take the best. So it saves you a lot of work. And classify does exactly the same. So classify is AutoML. If you want to see what classify did, take the first element, because in that corner in C, it specifies what this classifier was doing. It's a lot of information. Oh, I'm still reading these images, so let's stop this. If you Alt point, it stops it. And now we read what classify has been doing. Okay, and now you see it took a lot of data. The best model information is all this. It's an amazing amount of data. I'm not going to discuss it for you, but if you want to look inside deeper, I really, really, really want to know what happens on the tiniest detail. It's all there. It's way too much for the few minutes I have, but you see the point. Okay, I stop here this first lecture. You can do lots of other data. For example, you can read molecular data in Mathematica, and then it reads protein structures. So in this case, it reads protein data, and it has these sequences. And now you get these incredibly long sequences, and this is the model. And this model, you can rotate it, so it has all these fancy things. And you can learn which molecule is what, so you can put not only images in your classifiers, but you can complete molecule data, DNA strings, you name it. So it's pretty versatile. And Mathematica is fast, and I want to end this. So suppose I have a big matrix of real numbers between 0 and 1, and I make the matrix 10,000 by 10,000. That's a big matrix. Yeah, that's, what is it? 100 million entries. And it's a dense matrix with 100 million images. And this is another one, also with 100 million data. And then I do the dot product of these two matrices. So this is quite a big operation. Yeah? It's a lot of work. And this is important. This means a semicolon. Do not print all these images, all these numbers to the screen. If you forget it, you get, it really prints it to the screen. But in this case, we have quite a lot. And then I had absolute timing. So how long does this take on this computer? Of course, it has to generate them. It should be faster. Okay. Anyway, 14 seconds for this incredibly big operation, and I invite you to do the same in the break on your computer or at lunchtime. Just take 100 million matrix with 100 million matrix and multiply them. And probably it will be fast because every language has this underwater coded there. And
computer on GPU or CPU?
this is all done on the GPU. Anyway, I have so much to tell that I probably will not cover everything. Actually, I'm pretty sure I will not cover everything. But all the notebooks that I was preparing are available for you, so you can download and see them in more detail. I have 4 minutes, 3 minutes left. It's too little to start the next notebook. So let's use some time for questions. What I did in this hour was actually very basic. It was more to introduce you to the use of a new language for you, how you use these brackets and things. And in the next lecture, I give you a quick lecture. Maybe I can use a few minutes for that, how to program in Mathematica. That's just a few minutes left. Learning Mathematica in a few minutes, in 15 minutes. Most of it I already told you. And otherwise we use it in the afternoon session. The basic rules are brackets, but what is most important is if you use the here special characters, you use the escape key, that's the upper left key, and then you type a P and escape again. So if I type escape and then the P and then another escape, I get the Greek letter. So I can escape capital P, I get the capital Pi. Escape inf, I get infinity. Yeah? Escape A, you get alpha. So it's very nice to do that. And with this control, you get lower scripts. You can make n to the power of 17. You can make square roots by control 2. So it's very nice to write mathematics as it should be. If you want to write an integral that's more complex, you have these palettes. And the basic math assistant is here. And you can just say, I want to have an integral. Well, integrals are here. And then you say, okay, I have to have this integral here. Okay, put it in there. And you say this lower is minus, and then escape inf. From minus infinity to plus infinity. Yeah? And then you say, I have e to the, or let's say e to the power of minus x square to x. You see, now I have, this is real mathematical notation. And if you press shift return, because that's how you can have a multi-line input, it calculates it. And you see, it has now integrated this integral. And anything you want in mathematics, it's in there. And here I want to end. And see you later this afternoon. And then we go deeper into first principles.